Okay, so thank you very much for Marek for inviting me for this opportunity. So because for short time, I'll do very quickly. So today I'll give a talk on this our special purpose computer system for molecular dynamics simulations. So the newest version is MDGRAPE-4A. So maybe you know very well about, many of you know very well about molecular dynamics simulations. Of course, we calculate motion of atoms in molecules by integrating Newton's equation of motions. And as you know, this time step is usually femtosecond, and we are targeting for this microsecond to millisecond range, so or even longer. So it takes a long time to do such simulations. So our main target is proteins and also other biological molecules. And target is to understand the control mechanism in proteins and soft protein complex on or large scale structures of proteins and biological pathways or genome structures. And of course, we sometimes we have to study intrinsically disordered proteins like amyloid fibrils. And then we want to study some phase transition in such disordered proteins. And in future, this cellular rheology will be very important. And recently, liquid phase separation in cell is very important in genome transcription control. So this kind of target is very important in now and in future. So all targets requires much more computational power for longer and larger simulations. So, but there is some scheduling challenges because this molecular dynamics simulation is, of course, it costs computationally high cost, but rather low cost compared with other simulations like quantum chemical calculations. So typically, it costs about 30,000 flop per particle per step. Then if the system size is on order of 100,000, then it corresponds to 3 gigaflops per step. So if we have a 3 terahertz effective performance machine, it corresponds to 1 millisecond per step. So we can do simulation of 200 nanoseconds per day. I think it is already possible currently. But if we bring 3 petaflop machines, then it corresponds to 1 microsecond per step. So it corresponds to 200 microseconds per day. So this is very difficult but important. So this is only achieved by Anton system. So anyway, this protein molecular dynamics can't be accelerated by conventional supercomputers now due to a bottleneck in parallelizations. So the example is I will show some movies. This is. Oh, sorry. Oh, now this one. So this is we finished some 10 microsecond simulations of coronavirus. This is main protease, dimer of main protease of coronavirus, and we recently finished this 10 microsecond simulations by about less than 10 days using our newest machines. So we can calculate about 1 microsecond per day. So this kind of simulation can be done very rapidly. So you can see this. This is the active site of proteins. Then you can observe this change in this drug target pocket. Okay, so this coronavirus trajectory we published Mendeley data, so you can check, you can download it from Mendeley data. So currently we are developing special purpose machines. So this is because mostly for 3 reasons. First is of course increase. Currently we have some barriers for performance growth of supercomputers. First is increasing degree of parallelism. And second is power density. And third is the end of Moore's law. So special purpose approach can relax these problems. So I think this kind of specialized approach is one of the key technologies, as well as quantum computing and neuromorphic computing. I think the most important bottleneck is due to this too high degree of parallelism. As you may know, this speed of CPU core reached sharing around already 15 years ago, around 2006 or 2005. Then after that, the clock speed becomes almost constant, and performance gain has been achieved by parallelization of core. So, as you know, this current top supercomputers has millions of cores. That means a million instructions to be dispatched simultaneously. But since, for example, in case of molecular dynamics, the number of atoms is not so high, so we cannot dispatch million instructions efficiently. So there is some limit. So if we have very high parallelism, in case of weak scaling, this is simple. Then we, for example, if we like to create great walls, then we can use some kind of human web sweeper search. Then now we can work in a different position to make this wall. But if we want to solve a small problem faster, in case of strong scaling case, fine orchestration is necessary. So each core or each unit have to do different things. And it's very difficult to do such things in the general purpose machine. So we use dedicated computing to solve this. So we started GRAPE project already in 30 years ago. So this is an acronym of Gravity Pipe, because it started as a special purpose computer for astrophysical n-body simulations. But of course, this astrophysical n-body simulation is quite similar to molecular dynamics. Also, it's a classical particle simulation. Then we expanded to molecular dynamics. I think our approach is one of the pioneers in heterogeneous computer systems, like GPUs. So we send some data to GRAPE systems from host computer and get results back. This is the history of GRAPE computers, and this is GRAPE for astrophysics, and this is also GRAPE for astrophysics at higher precision. And red one is GRAPE for molecular dynamics, and this is the top supercomputer line. So this is, we won 8 Golden Bell Prize in total. But as you may know about Anton systems, and they develop a very fast specialized machine for molecular dynamics simulations. So they developed the SoC, System-on-Chip, with a specialized purpose pipeline, and general purpose CPU core, and specialized network. Anton's basic elements are very similar to MDGRAPE, but the integration is very important. So they show the importance of optimizing the communication subsystem and also this job control subsystems. And Anton 1 achieved 20 microsecond per step, correspond to 10 microsecond per day, and Anton 2 achieved 2 microsecond per step and 80 microsecond per day. So we started to develop MDGR4 and MDGR4A after that. And this is a specialized machine for molecular dynamics simulations. But previous GRAPE systems, its basic idea is just specialize the only important part, like non-bonded post calculations. But to catch up Anton systems, we need to specialize as much as possible. So we develop system on chips that integrate non-bonded engine and long-range engine and general-purpose processor cores and network and memory. So everything is packed into the single SoCs. So what is specialized in MDGRAPE-4A is first is non-bonded interactions. This is already done in early GRAPE systems, but we also added a long-range part of Coulomb. So we support multi-level summation method and charge assignment and back interpolations, and network with grid compression, which is needed for multi-level summation method. And we also added some kind of particle management. So now serial index support is embedded in memory as a hardware. And for example, a lookup table to obtain particle address from particle ID. This kind of specialized hardware has been embedded. So these are all new parts of current GRAPE systems. So this normal pipeline calculates some such kind of functions on the Coulomb force and van der Waals force and potentials. So this produces most of our computational powers in our chip. So single chip has about 2.5 teraflops equivalent. These are deep pipelines, so with dedicated unit. So about 30 stages of pipeline we developed. And for the memory and general purpose core part, we use RISC-V processor, which was introduced Carissa in previous talk. We expanded it with SIMD. It operates at 0.6 GHz. So our processor has 32-bit integer. It's very standard RISC-V. And extension, as an extension, we have 128-bit four-way fixed point integer SIMD. And we have a 64 kilobyte local memory and 32 kilobyte instruction cache per core. So our core is designed by Synopsys ASIC designer. And actually, our processor core is not fully compliant with RISC-V, so some instructions are not implemented. And we have embedded 256 kilobytes shared memory per two cores and DMA controller and on-chip network. So this is diagram of memory and processor block. There's this 5 core. So 2 core are embedded in single block. And these 2 core shares one large memory of 256 kilobyte and some scratch pad memories and DMA controllers and some interface to network unit, pipeline unit, and on-chip network unit. So in total, we have 8 such blocks that correspond to 16 cores. So as I told you, our memory has some special functions. And for example, in memory, we can do some kind of accumulations. So many of the synchronization between cores needed for molecular dynamics is solved by atomic accumulations. For example, in force accumulation, we need to calculate sum of forces by different units. And in total, we get final forces for each atom. Then in normal multiprocessor, we have to repeat lock and read and add write and lock. And we need to repeat this. So our memory supports atomic accumulation at memory. So just a single accumulation DMA finishes this kind of additions. So we can decrease time for synchronizations. Also, the similar thing happens in the particle management. So usually we use so-called special decomposition of atoms into each cells. So of course, the atom moves, so we need to migrate atoms in every 1 to 30 steps. So in every these steps, we have to redivide atoms into cells based on new coordinates. So since particle is coming from neighboring cells, so several cores, including the other chips, may add atoms to cells. So again, then this is asynchronous addition happens. So we have to repeat lock, read atom numbers, and write lock, unlock. So our memory has specialized functions. So to support atomic addition of atoms to a cell. Then, sorry, this allocation of, so it allocates atom memories, and it also has a management unit for free space. I'm sorry, this is maximum number of atoms is not 16, but 64. So we allocate the unit of 16 atoms, and in total, we can allocate 64 atoms per cell. And this we read, we have some specialized DMA command to read all atoms and send all atoms to some network, or this kind of cell number-based specification is possible. Anyway, this kind of cell memory can decrease latency in the program. And for long-range Coulomb calculations, we developed a new novel algorithm to calculate long range effectively. So this is in preparation. So we will submit this paper quite soon. So this is based on a multi-level summation method. But we improved our approaches and the method, and we can do this convolution by separate convolutions on different axes, X, Y, Z. So our algorithm can apply not only for molecular dynamics, but also some other applications with three-dimensional convolutions. And we implemented this algorithm to the hardware. For example, our network unit has a uniaxial convolution unit. And also, we have a specialized FPGA with 16 by 16 by 16 FFT based convolutions calculations. And we also have spline-based charge assignment backward interconnection hardware in SoC. So finally, this is the final form of our system-on-chip. It's very complicated. So our SoC has very different combination of very different units. So this is the general-purpose core part and network unit, and some control processors and on-chip network, and this is host interface, and non-bonded pipeline and long-range calculation part. So this MDGRAPE-4 system has 512 SoCs. Maybe we'll explain this in this next chart. So our system has 512 SoCs in 8 by 8 by 8 topologies. So in one direction, we have 12 lane of 60 GBps. So it corresponds to 7.2 gigabytes per second for peak performance. And for little unit, we use optical interconnections. Then this is photographs of the system. So in total, we have 4 pedestals and 64 of 2U box, and this orange line is all optical fibers that connect between this unit. And there is some FPGA unit here to calculate fast Fourier transforms, convolution based on fast FFT. Then for this, we have developed this kind of board, very large board. Here it's SoCs, and this is optical socket for optical unit, and then some power supplies. So the current status, we finished this. Our hardware main system has been completed last year, March, and FPGA part for long range support has been completed last September. And currently, GRAMAX is running, so with constant temperature, constant volume ensemble, and we have confirmed the accuracy is comparable with single precision GRAMAX. And we are continuing our performance tuning. So currently, our performance is around 1 microsecond day for 100,000 atom systems. So our target was little bit faster. So initially we targeted around 4 to 5 microseconds a day. It's still, our performance is behind of these Anton systems. I have to admit that, yeah. But I think for us it was very great, big step to reach to the successful operations of this kind of complex SoCs. And currently, we are developing a constant precision ensemble software, and it will be ready in 2 to 3 months. So what is special in our SoC is, of course, we integrate various units, and general purpose part was this pipeline part and this long-range part. So this kind of combination is, of course, very popular in SoCs. But the difficult point is our SoC, these all units have to work simultaneously in high efficiency. So this is very different with normal SoCs in smartphones or this other applications. So currently, such an approach can be taken by only us and these shows. So for the next generation development, I think it's a little bit difficult to make different with Anton, because both machines are based on deep system integration using normal technologies. But in other sense, it's possible to catch up them because both are using very standard technologies, semiconductor technologies. So our goal is user-friendly and easy to introduce systems. So our current system is very large and very high cost. So production cost is about $3 million because our system has 512 chips. So in the next development, we have to build systems with that operates from very small scales, like 8 chips, and our sweet spot. The sweet spot of next system will be 64 chip systems, and we are targeting this similar performance with Anton 2 system can be obtained by 64 chip systems. Then current MDGRAPE-4A is based on the 14 nanometer process, rather old technologies. So by use of 12 nanometer process, we will obtain around 10 times more performance and 16 times more memory per chips. Then we can achieve around 50 teraflops equivalent performance. Then currently we gradually started the development of MDGRAPE-5. So overall, we will rewrite mostly in teaser language. And the network for network, we improve network to achieve smaller latency. Current network latency is single hop memory to memory latency is about 200 nanoseconds. So this is already much smaller than general purpose network, but still we like to improve to hopefully below 100 nanoseconds. And for general purpose cores, we need to add some engine to accelerate bonded interactions, not only non-bonded interactions. And currently we plan to expand RISC-V rocket boom core developed by Berkeley, not using Synopsys HIP designers because of the performance reason. And we will add some hardware to support data flow style parallelization to minimize latencies. So the whole software part, and then current our problem is the software base for general purpose processor and MDGRAPE is different. So we like to make some common software base. So for this, even for this general purpose conventional PC clusters, we can use some event-driven data flow style programming. So with some simple network models, or maybe some wrappers or RPCs. And we plan to use some modern language. So currently we are using C, but maybe we also investigating some domain-specific language approaches using C++ or Rust or NIM. So this is the evolution of this molecular dynamics processors. So in old MDGRAPE, then it only has some pipelines for the non-bonded calculations. But MDGRAPE-3 has some support for PME, particle method abort. But Anton 1, they introduced quite a lot of functions into LSI. So we try to catch up with by MDGRAPE-4, but unfortunately it does not work fully. So we developed MDGRAPE-4A. So MDGRAPE-4A has many support, including this event management or particle management. This improvement was very important. So in MDGRAPE-5 also we will continue, and we add some bond engines to accelerate bond calculations, and we will try to enhance the event management. Then, so this is actually, again, this MDGRAPE-4 is a little bit slower than this, but at this moment, but our target is in MDGRAPE-5, we can achieve about 100 microseconds per day with 64 chips systems. So anyways, by general purpose machines, so this is prediction of some calculation time per day on general purpose supercomputers. So this is almost correct, but still a little bit slower than maybe expected than this. Yeah. Anyway, it's very difficult to catch up Anton type machines by general purpose supercomputers. So we will continue our development, hopefully. So the goal of molecular dynamics simulations with classical computer is maybe around 2028. Then already Moore's law has been ended. Then we cannot increase further. At that time, I think we can run millisecond simulations of 100,000 atom system for 2 days. It corresponds to 1 microsecond per step and 5 femtoseconds per step. Then this kind of simulation can be achieved by small computers. So we can do 1 millisecond simulation times 1,000. So in total, we can run 1 second scale simulations in total. Then we can reproduce many slow dynamics of proteins, including folding dynamics or complex formations. So we can solve many of questions by computers. And you can also achieve 10 millisecond simulations with millions of atoms to study cellular rheologies. Then we can, molecular dynamics will become basic tool for studies of small scale systems using special purpose approaches. So that's all for my talk, and this is final slide for the acknowledgement. This is all our team to develop our machines, and so we are a very small team, but we can develop such machines. Thank you for your attention.
Makoto. Now we have the time for maybe 1 or 2 quick questions. Do we have questions from the audience? So we have a first question from Krzysztof Hałagan. What is the power consumption of MDGRAPE-4A, and is it air-cooled?
Okay. That's, sorry, I forgot to, good question. I forgot to include it. So power consumption is about 60 kilowatt for total systems. So it is air-cooled currently, yeah. So it corresponds to around 1.3 petaflops performance. So power is rather low.
Right, very impressive. Do we have, how about the GRAPE-5?
Okay, so for MDGRAPE-5, so we proceed from, currently we use 14 nanometer, and yes. MDGRAPE-5 will move to 12 nanometer, or of course, if we have money, 7 or 5 nanometer. But if we move to 12 nanometers, the power can be decreased by 10 times, more than 10 times, I guess. Yeah.
I can't see any more questions, so thank you very much, Makoto-san.